Solving basic trig equations. So here's our solving steps. Step A, whatever you're given, rewrite it so there's a single trig function, a single variable, an equal sign, and a number. For that single trig function, we want it to be only sine, cosine, or tangent. Then, using a picture, we're going to find the solutions to that equation within one period of the function. Now that means between 0 and 2 pi for sine and cosine, and between 0 and pi for tangent, because the period of the tangent function is just pi. If needed, we'll add multiples of the period to those basic solutions to find all the solutions. And finally, it's very important to read the directions. Do we want exact answers, or do we want decimal approximations from the calculator? Are we working in radians or in degrees? Do we want all the solutions or only solutions in a given interval? Our first example problem says solve for x. We want all exact radian solutions. Notice that each word is important. All, not just a few. Exact, not from the calculator. Radians as opposed to degrees. Well, let's follow our solving steps. I'm looking at this equation, 4 sine x minus 3 equals -1. I need to get that sine x by itself. So of course I'm going to add 3 to both sides, and then I'm going to divide both sides by 4. I'll reduce the fraction, and I end up here with exactly what I wanted. A single trig function, sine, cosine, or tangent, a single letter, an equal sign, and a number. So that was the end of step A. Okay, step B. I want to find the solutions to this equation we just wrote down within one period, between 0 and 2 pi, one full revolution. Well, it's very helpful in these problems to think about our all students take calculus device, because where can the sine ratio be positive? Well, of course, everybody's positive in the first quadrant, and then the sine ratio is also positive in the second quadrant. It's negative in these other quadrants, so I know that within one period, within 0 to 2 pi, there are two possible angles, right? This x here is an angle. There are two possible angles that have a sine ratio of 1/2. Let's draw in those reference triangle pictures. One of them's here in the first quadrant, sine ratio opposite over hypotenuse. The other one would be very symmetrical and over here in the second quadrant, again opposite over hypotenuse. One of our angles is this angle right here. The other angle is this angle right here, right? We have a first quadrant angle and a second quadrant angle. Well, we're looking for exact solutions. That implies I don't need the calculator. I can do this by hand. I must therefore have either a 30-60-90 or a 45-45-90. That's all I can do by hand. When you see a 2 and a 1, of course, you realize, oh yeah, this is just root 3 or negative root 3 over here in the second quadrant, which means this little angle is 30 degrees. This little angle is also 30 degrees, the one opposite the 1. By the way, we haven't mentioned the sine inverse function. I mean, isn't the sine inverse function what we use if we're given a ratio and we want to figure out the angle? And the answer is yes. Just remember, though, that the sine inverse function is limited. Sine inverse only knows about angles between negative pi over 2 and positive pi over 2. So the sine inverse function would know about this little first quadrant angle. It would not know about this second quadrant angle. That's why the picture is so important. Well, I think we're ready to write down now our solutions. I am working in radians. So clearly that first little angle in the first quadrant is 30 degrees, which in radians is pi over 6. And let's see, the second angle I want is this angle. Well, obviously, if this is 30, then this big angle here must be 150. 150 degrees in radians is 5 pi over 6. Those are the only two angles within one revolution, within one period, that have a sine ratio of 1/2. Okay, now step C. Step C addresses how to take those two solutions and turn that into the infinite number of solutions that exist for this equation, because we do want them all in this problem. Well, all that you would have to do to find other solutions is simply rotate around beyond one rotation. I mean, if I rotated 360 degrees plus another 30, of course I'll land at the same spot. I could rotate 2 more times around or 3 more times around. I could rotate around counterclockwise, etc. Well, the way to capture them all is simply to add multiples of the period. In our case, that would be 360 degrees, or in radians, 2 pi. Now, the way we're going to express multiples of the period, we'll use k times 2 pi. Or this is usually simplified as 2k pi, multiples of 2 pi. You might see another letter in there instead of k, like n could be used. But the point is, whatever letter is used, it stands for multiples of the period, multiples of 2 pi. What we're saying is, some of the solutions are pi over 6 plus multiples of 2 pi. Notice that k stands for an integer, which means it could be negative as well as positive. You could rotate around counterclockwise. You can rotate around clockwise. It doesn't matter. You can add or subtract any multiple of 2 pi and you'll get another answer. The other group of answers would be the 5 pi over 6 answer plus multiples of 2 pi. This statement then, what's in this box, represents all the infinite solutions that exist to this equation. And so this would be my final answer. Thanks for watching.